Second question. A proton and an electron traveling along parallel paths enter a region of uniform magnetic field acting perpendicular to their paths. Which of them will move in a circular path with higher frequency? We know that frequency of a charged particle with which it revolves in a circular path in magnetic field is given by F equals BQ by 2 pi m. For proton, charge is E, mass is mp, mass of proton. Then frequency of the proton is Be by 2 pi mp. For electron, Q is equals E, same as that of proton. M equals mass of the electron, me. Then frequency of electron in the magnetic field is Fe equals Be by 2 pi me. We know that mass of electron is less than mass of proton. That means Fe, frequency of electron, will be higher than frequency of the proton. That is the solution. Next question. What are wattful and wattless currents in AC circuits? We know that in general, in an AC circuit, current and voltage are out of phase. There is a phase difference between them, except in the case of resistance. So generally there is a phase difference. So we draw current vector and voltage vector making an angle between them, and that angle is the phase difference. Usually we draw current as the baseline. Now for the time being, let it be V. This horizontal line represents, let the horizontal line represent voltage. Then current will be making an angle phi with this voltage line. That means there is a phase difference between current and voltage. This current, this is a general case. This current vector can be split up into two components. One is I cos phi parallel on the voltage line. That means I cos phi is in phase with the voltage, just like the case of ohmic resistance. The other component is I sin phi. This is sine. I sin phi, not cos, sin phi. This I cos phi is in phase with applied voltage. That means that component is responsible for consuming power, because power is expressed by the formula V into I cos phi. So I cos phi is the component of current that consumes power. So I cos phi is called the wattful component of alternating current. I sin phi is perpendicular to the voltage vector. That means the phase difference between I sin phi and voltage is 90 degree. Wherever phase difference is 90 degree, power consumption is zero, just like capacitor and inductance. So I sin phi does not consume power. So I sin phi is called the wattless component. Remember, I can be split up into two components, I cos phi and I sin phi. I cos phi is in phase with voltage, that is on the voltage line itself. So I sin cos phi is called wattful component because it is the component which consumes energy. And the other component I sin phi is called wattless component. Next question. in a potentiometer arrangement for determination arrangement to determine the EMF of a cell, the balance point of the cell in open circuit is 350 centimeter. When a resistance of 9 ohm is used in the external circuit of the cell, the balancing point shifts to 300 centimeter. Determine the internal resistance of the cell. Now this is a brief diagram. This is a potentiometer, and of course there is a storage battery, a rheostat, etc. We don't draw that details in problems. So AB is the potential. This is at high potential or positive. This is negative. This is the EMF whose internal resistance is required. And there is a key, external resistance, galvanometer, and jockey and so on. Now, if this key is kept open, there is no current flow in this circuit and the battery is said to be open. Now, when a battery is open, its full EMF is available externally. So, its full EMF gives the balancing point. Let that balancing length is given. We have the basic equation of potentiometer. Balancing EMF E equals small e into balancing length, where small e is the potential gradient of the potentiometer wire. Here L is 350 centimeter. So E equals E into 350 centimeter. That's equation number 1. Now when you close this key, this cell will send a current through this R, then its terminal PD will fall below the EMF, and the terminal PD balances a segment of the potentiometer wire. The terminal PD V equals I into R. So V equals I into R, where I is EMF by total resistance, E by capital R plus small r into capital R. This is V. This must be equal to E into L, gradient into balancing length, or this capital E into capital R is given to be 9 ohm by 9 plus R equals E into 300. You can solve these equations to get small r internal resistance. You divide equation 1 by 2, then you get 9 plus r by 9 equals 350 by 300. Just you cross multiply this, you get 9 into 300 plus 9, 300 into r equals 9 into 350. You take this to this side, then 9 into 350 minus 300, that is equal to 300 r. This is 50 into 9, from which r equals 9 into 50 by 300, that is 1.5 ohm. That's the answer.